Okay, we're going to talk about lungs. So let me get my pointer out. So we're going to start off our discussion of lungs by talking about Taffy. This here is Taffy. She is or was in 2001, she was the fastest cow in the world, and I actually helped train her to do that. So this is Brian Nielsen. Brian Nielsen was the equine science major at Michigan State. Taffy was one of the cows on our research trial to see whether exercise helps the transition cow. So training the cow, doing exercise, putting the animals on a hot walker, getting them aerobically fit? Do they transition better? Less problems with ketosis and things like that? The answer is yes, they do. Well, Taffy was one of the animals on that trial, and she was very much an outlier. She had a set of lungs on her where she just wouldn't quit. So we did the hot walker training every other day. They got out and they walked a mile around with the hot walker, and then they put them at various intervals. They put them on a treadmill to do a stress test. Taffy was phenomenal in her ability to keep going. She just was a machine. She kept her lactic acid very low for a very long time, and that all points to a remarkable ability in her lungs. She had the ability to get that oxygen in and use it in her body. So when she was up for auction, Professor Nielsen bought her, trained her for saddle, and she won the inaugural world's fastest cow race in mid-Michigan. There's some links down here that talk about that. A video, you can see Taffy winning the race. You got the big picture of milk there, and there's an article about all that if you're interested. But that's kind of an aside. Let's talk about lungs. So we're going to ask the question, how does a cow breathe? We're going to answer this four different ways, which sort of make make up our objectives for this section. We know the parts. We want to know the parts of the lungs in their order. So how does air flow through the system? We want to know how breathing works. What are the mechanics of that? How does air get moved in and out in a mammal? What are the lung volumes and capacities, and how do they inform us about breathing? And then we want to know about our oxygen and carbon dioxide exchanges. How does oxygen get to the tissues, and how do we get carbon dioxide out of the tissues? How does it move through the body? So we're going to start with the parts. How does a cow breathe? What are the parts that the air moves through? So we're going to start with the parts in the head. We're going to go down the trachea, and then we're going to get down into the lungs. Start with the nose and mouth, work our way through the system, and then get down into the various parts of the lung. So we have the airway beginning, and then we have the lungs, and the muscles of respiration are going to move and stretch the lungs out to create an air exchange, a billowing effect. So from the Atlas of Bovine Anatomy, we're going to come in through the nose or the mouth. We're going to go down to the larynx. We have our trachea over here. We close up, the esophagus goes off to the side. We come down in the trachea and we move on to the lungs. So the lungs of a bovine are kind of laid out in 5 lobes. So we'll see a better view of these. But we get down to that first rib, and then we have the end, one of the end ribs there, and we have the lungs stretching between those. We have 1, 2, 3 lobes on the left lung. We've got the diaphragm that's going to come up and move up and down, or I guess forward and backward, caudal, cranial, anterior, posterior, um, superior, inferior, one of those ways, and stretch out our lungs. We have the cardiac notch where the heart sits. So the number E down here is the heart. So that's sort of where the lungs are in profile. I think this is a little farther back on a scale, but basically the lungs do just barely come back to one of the lower ribs. We take a dorsal view, so we're looking down on the lungs. We're going to have 1, 2, 3 lobes here, 2 here. Heart's going to sit over underneath over here, 1, 2. So 1, 2, 3, 4, 5 lobes. Again, from the Atlas of Bovine Anatomy, you should have that full page there. We're going to come down a single trachea. So from the head, the mouth, the larynx, the common area, we come to an area that just has air moving through it. So this is a rigid structure. I like to think of it as kind of a vacuum cleaner hose. It's going to resist collapse. It's rigid. It's going to keep its shape. Then we first branches we have are the bronchus. Each one is an individual bronchus. Or we have the bronchi, for if we say them in plural. So we've got 1, 2, 3. We go a little farther down, they're going to branch off more. And then we get down toward the end, we have the bronchioles. So we got mouth, nose, larynx, trachea, bronchus, bronchioles, or bronchi, bronchioles, depending on how you want to look at it. We can see this is a human setup, and we're going to again focus on those different types. We're eventually going to get down here to the end of the line in the alveoli. So you're looking at a frontal view of a human. The heart sits right here. You've got the cardiac notch there. Diaphragm on us sits underneath it. You've got liquid there that's going to connect or make the lungs stick to the diaphragm. So you've got 2 lobes on this side, 3 lobes on this side, and again, the trachea. The trachea, the bronchi, and then as we get down there, bronchioles. All these are rigid. They do not collapse. They do not change in diameter. When you're breathing, it's the other stuff toward the end, the alveoli, that are going to change in shape and size. These remain open. There are a certain amount of secretions in there that can cause problems. In asthma, there's a certain amount of constriction where you can have things collapsing down or tightening up, but for the most part, they are always open. Here's another looking at the human, and we're getting down here to a closer look at the parts. So getting down here in the corner, we're going to have the lungs are not going to be, at least in a normal situation, attached to the outer wall. We need them to slip and slide. And I like to think of 2 plates of glass with water in between them. We can slide those plates back and forth pretty easy. But if you try to lift them apart, there's that surface tension, that suction, that's going to prevent that. So that's how the wall of the lungs sticks to the wall in the rib cage here. So you've got that space. As we work our way down the airways, we're going to get down to the end, and we've got the alveolar ducts and the alveolar sacs. And you can see that we talked about a net of capillaries that bathe highly interconnected space that bathes the end of the lungs. So we have these groups of grapes here. Each is an individual blind sac covered with a capillary bed, and the air moves in and out. These parts of the lungs are very elastic. They're going to stretch open to fill up with air and then collapse down to eliminate air, unlike the trachea, the bronchus, and the bronchioles. So closer look at that same diagram. Again, you've got artery coming down. You go to a capillary bed, and then you've got a vein going back. So each alveolus set of alveolar sacs has its own capillary bed surrounding it. It's got its own capillary feeding it and draining it. So you're going to form that net of capillaries that's going to be around the outside of those alveolar sacs. And then the air hopefully moves in and out. So we have a net function of fresh oxygen coming in and expelled carbon dioxide moving out. Another kind of more simplified diagram, larynx, trachea. You've got the bronchi, and then you're working down to those alveolar sacs. You've got the ducts and the sacs. Then we start the capillary bed, and then it covers over these areas down here, cluster alveoli, one individual alveolus moving through. It's down here in this circle where the air exchange happens. It doesn't happen up here, doesn't happen in the trachea, the bronchi, the bronchioles. So showing that coming in, we have the pulmonary artery coming in. We have that capillary bed surrounding each alveolus, and then we have the return, the pulmonary vein that'll eventually collect in the pulmonary vein. So you have the different muscles around here that'll open and close. The smooth muscle will open and close the bronchioles as is needed. But again, all the air exchange occurs down in these more or less full spheres, although there's kind of a bubbly kind of appearance to it. Not all of them are full circles. Another diagram of the same thing, showing the blood exchange a lot better. So you've got we've got looking at the blood pour coming in the artery. Blue is our oxygen pour. We're going to, as the web, as the net across there, we're going to enrich, and the vein going back is going to be filled with oxygen-rich blood. So each alveolus has got its own capillary bed. So parts of the breathing, we're going to mouth, nose, pharynx, larynx, trachea, branch off, bronchi. There are a number of different segments of those. We won't worry too much about them. We got the bronchioles, all in black here about moving air. We're trying to transfer air from outside to inside. So it's best that these take up as little volume as they can, because the gas exchange cannot occur till we get down to these red parts here, the alveolar ducts and the alveolar sacs. So this is where we have to get the fresh air in, the bad air out, and this is the area that's got to change in size. This is more a constant dead space where no air is exchanged or gas is exchanged. Air moves through, but does not diffuse across. Those things are too thick for that. So we know the parts. Let's kind of move on to the mechanics. How does a cow breathe? So we're talking about the muscles involved with the breathing. You have the diaphragm. Diaphragm is, for us, it's underneath the rib cage. Cow, it's at the back of the rib cage, and its major function is to draw air in. It's a major inspiratory muscle. Muscles do their work when they contract and when the diaphragm contracts, it becomes shorter and therefore flattens out and pull the lungs down. So therefore pulling air into the lungs. The external and internal uh, intercostals each move the rib cages in two different directions. So the external, they're going to pull on the rib cage and they're going to open it up. So you can think about it kind of in your back. You're going to open up the rib cage. If there was no sternum there, it basically fly open. The internal intercostals are about closing the rib cage down. Now, the rib cage itself doesn't move all that much because basically we've got bones. The only elasticity we have is in the connections in the ribs, particularly here in the front, and then the false ribs down at the bottom. We have some opportunity to move a little bit of those. Depending on how much they stretch, the rib cage can open and close a little bit, but most of the breathing comes from the diaphragm. We also have the abdominal walls, the muscles of the abdomen. They can help push air out. They're going to push up on the diaphragm as it relaxes. They're going to help push the air out. So, again, looking at our parts, we've got the lungs here, we've got the more or less rigid rib cage, and then the diaphragm is going to do a lot of the work about stretching and these lungs out and drawing air in. So as the diaphragm contracts, it becomes shorter, a straight line, and it lays flat here and thus pulling the lungs down. We'll see that in the coming slides. So here's kind of how the muscles are here. If you like ribs, this is sort of where it all comes from. You've got the intercostals on the inside. You've got the external on the upper half here. So you have muscles that are going to pull the rib cage here, stretching this cartilage, this connective tissue here and here to open up the lungs. It's also going to move this plate out forward. So you've got the externals are going to open up the rib cage. The internals are going to collapse that down. So we're going to try to stretch, open up the rib cage. If you've ever seen an animal that has really bad pneumonia and their lungs are really, really damaged, you'll start to see an animal breathing very hard. And over time, you can see, I've only seen this once or twice in my life, where the animal spends all day breathing so hard that these muscles will start to fill up and you can see them flex on each breath the animal takes. It's trying so hard to live on a limited lung that it really has to collapse the lungs down. It really has to open the lungs up as much as it can. So these muscles get a workout. They start to develop, and you can see them flexing each time an animal breathes. The intercostals, external intercostals are in those two locations. So one thing to remember, most of A&P is everything moves from a high to a low. Now what we're going to do is start with a resting position. So everything is relaxed. The air inside the body is equal to the outside of the body. The lungs are stuck out to the ribs. And again, that's that glass on glass with water between it. If you want to go and do a hands-on thing, take two pieces of glass, put a little water between them, push them together, and then try to pull them apart. You can't do it. You can only slide them apart. And that's how the lungs stay inflated, how they are attached to the inside. If air gets into this space, the lungs are no longer attached. If you want to break apart two pieces of glass that have water in them, the easiest thing to do is shoot air in between them. Once they are no longer stuck, this elastic material collapses back and shrinks and separates, and that's called a pneumothorax. We've got air in the lung, air in the rib cage, in the thorax, and the lung collapses. So if you've heard, like on the medical shows, oh, he's got a lung collapsed lung because his trachea is deviated. So one of these is no longer stuck to the wall. There's nothing pulling it in that direction, so it tends to get pulled over here where the lung is actually stuck. So we've got intrapulmonary space. Inside the lungs is at atmospheric pressure. Outside air, inside equals outside. No air is moving during the resting state. Diaphragm is relaxed. The muscle is uh, lengthened out. Move on to the inspiration phase. When we breathe, we go from rest, inhale, exhale. Rest, inhale, exhale. So the first thing we want to do is inhale. So the diaphragm contracts, it shortens, it pulls down, it becomes shorter going across. That means the lungs sticking to it are going to go down with it. And with that, the chest can also move out. And what we've done is in these two lungs, we've created a negative pressure relative to the outside. The outside air is still at atmospheric pressure. We create a negative pressure or a vacuum. So it's not a big one, but higher air outside, lower air inside, the air moves in. So as we open up our lungs, we create that negative pressure. Air moves from a high to a low. We complete our muscle movement. We filled up our lungs. The events reverse. The internal intercostals are gonna collapse the chest. The diaphragm ascends. We can flex our stomach muscles to blow out. We collapse the lungs. We reduce them in size. The air pressure now is greater in the lungs than it is outside. Air moves, leaves the lungs. So we can see this kind of on the same slide. Inhalation followed by exhalation. So we've got the rib cage expands as the muscles contract. We lower the pressure in the lungs. The diaphragm moves down. The air moves in. Everything moves from a high to a low. Diaphragm moves up. We can see that in this particular thing there. The rib cage collapses. We increase the pressure. Air moves out. So we think about our muscles. We've got the diaphragm. That's going to be largely responsible for bringing air in. So as that muscle contracts, that if we ever got to see a dissection, that is usually one of the wow, that really looks cool. The inside of the thoracic cavity, how the diaphragm works to move the lungs in and out. Our externals are going to open up the rib cage, breathe in. Internal are going to collapse the rib cage, breathe out. And if we need some help relaxing that diaphragm, we'll get the abdominal muscles involved, helping to clean out our CO2 in our lungs. So one of the things we want to talk about here is snorkeling. If anybody's ever been snorkeling, snorkeling makes it a little bit more difficult to breathe if you're just using your snorkel. It's a lot easier than breathing water, but the snorkel extends our trachea, extends our transverse section of our lungs. And the downside of that is that we've got more dead space. We have more air that doesn't leave the lungs, that is more dead space. So you've got more volume that you have to move to get fresh air in. Your trachea is effectively 2 feet longer, and it's going to require a whole lot more effort to move that air in and out. So we're going to increase what's called our tidal volume that we're going to breathe in and out more. If you have a real interested, there's two things here to discuss the scientific what happens to breathing associated with snorkeling. Well, basically, we've made our trachea about a foot and a half, 2 foot longer. So we have to move that much more air to get stuff in to the lungs. And because we have to move air, it's going to require more effort. So those are two ways that snorkeling messes up with breathing. One thing I'll leave you with, I get the Smithsonian magazine, one of my favorites. From the National Museum, Smithsonian Museum. It's our national museums. It's called America's Attic. And one of the things they highlighted recently was the goggles from the first woman to swim across the English Channel. So, swimming from France to England across a very rough stretch of ocean that in the canal, lots of currents, lots of water moving as the tides come and go. And one of the things they notice here that she was a very um, strong athlete. This is 1926, and she had the remarkable ability to expand her chest 8 inches when she breathed in. So you compare that to her contemporaries, Babe Ruth, a famous baseball player, and then prize fighter Jack Dempsey. They could only move their ribs 4 inches, expanding. So one of the reasons she appeared to have been such a great swimmer was she probably had a more elastic rib cage. Therefore, she could open up her lungs more, stretch her lungs more, bring more oxygen in with each breath. So I thought this little box here might be something of interest to you. So one of the reasons she was good at what she did was her ability to bring that oxygen in. One of the things we're going to do here to demonstrate moving forward is show you how breathing works using a syringe. And the plunger on the syringe is going to represent the diaphragm. The sheath or the outside edge there is going to be our rib cage. So if you can find a syringe, we're going to demonstrate that in the next day or two for you.